Good afternoon. My name is Apostolos, or Tolis Christou, as I'm commonly known here. And I'm a planetary scientist. My main occupation is with modeling, so I spend a lot of time number crunching in the computer, but I do also do some observing, mainly for fun, but also I find that understanding how your observation helps you understand better the solar system is also a contributing factor, and of course with my background I can do that. Okay, so this is a light pollution talk, so I should actually show at least one image that's relevant to light pollution. In fact, the relevance of this talk to the light pollution issue is that the observations I'm going to show you were carried out from a location that suffer from some light pollution at varying degrees. For example, I have carried out some observations from the outskirts from Athens, which is deeply within the red. Okay. Also, I've done a lot of observing from here, from Armagh, which is in the boundary between the green and the yellow, if you like. And I've also done some observing from the north coast in County Donegal, which is currently in the black in this map and will hopefully remain so for the foreseeable future. Okay, now let's start with a nice image of a solar eclipse. This was taken by myself from Novosibirsk in Siberia last year. Now, what is a solar eclipse? It is basically the result of a dark body like the moon here, which I've outlined in yellow, passing in front of a light source, such as the sun. Now, the light source does not have to be the sun, though. It could be a star, as like that one over there. This is not actually a star, it's the planet Mercury, but for the purposes of this talk, we can safely assume that it's a star. Okay? Now, if you have a very small source, then you can count it with a very small bodies, such as an asteroid. For example, here I have an image of 2868 signs taken by the Rosetta spacecraft. You should actually appreciate this image because it's your taxes that paid for it. Okay, so I'll just make a very brief interval to show you a little movie of an occultation. Okay, I'd like you to pay attention. I'll show you basically a video, a very noisy video of a star field, and I'll ask you to pay attention to a star that's near the bottom of the screen. Do you see the star that actually goes out and comes back up again? That's actually what okay, just a minute. I don't know how many times I've actually opened this presentation. Okay, so this is how the event appears to the eye, and it's actually quite a profound experience, because stars are not supposed to go out like that. Okay, but it's also scientifically useful because if you time the disappearance and reappearance of the star, then the difference will give you an estimate of the size of that part of the asteroid that occulted the star. Now, if you have many observers that observe the occultation, then you can start having some idea on the shape of the asteroid. In fact, the resolution of your so-called People telescope depends on the number of observers that are available. In fact, there's an organization called IOTA, which actually coordinates such campaigns all around the world. This is the website of the European section. I'm going to show you an event that was covered by more than 70 observers in 2002. This campaign was also organized by IOTA. As you can see, we can actually make out mountains on this asteroid, and this is something that you can. It's actually impossible to do with ground-based telescopes, even with adaptive optics, I would say. Okay, now just a final note on that. Every year or so, you have an opportunity to observe an event that involves an object that's of particular interest in planetary science. Just a minute. For example, if it's a planetary moon like Charon here, a satellite of Pluto, if, for example, there's some question about whether there's an atmosphere around it or not. So if you actually observe, you can actually get yourself a paper in Nature. Right. Okay. There you are. Now, these are just a summary of my own experience with asteroid occultations. I started with visual timings, a telescope, at least one eye, and a stopwatch to time the disappearance and the reappearance. So my first success was with asteroid 514 Amherstia in 2002. I'm basically one of these Higgs cords, one of the bunch in the middle. And you can see how you can use the cords to start fitting a shape to the asteroids. And similarly for two subsequent successes in 2004 and 2005. The last one was actually observed with a 10-inch Crab refractor up at the observatory. And in fact, if it's clear tonight, which it might be, I'll be willing to open up the telescope for anyone wishing to have a look through it. Okay, now switching over to CCDs. So CCDs are cameras that are specifically made for astronomical observations. They are very light sensitive, so you can reach fainter stars. For example, here we had the opportunity to have an occultation of a star of magnitude 12 that was going to be hidden by asteroid Tyche, which actually means luck or good fortune in Greek. So we decided to give it a go. It was me and David Asher, who might or might not be in the audience. There you go, David. So the path of the occultation, which is very like the path of a solar eclipse, was passing through the northwestern part of Ireland. So we travelled to County Donegal with the CCD and a 6-inch reflector to observe it. This was the field that we saw. Tyche is in the circle here, together with the star that's going to be occulted. So the two are very close. You cannot tell them apart. Now, by measuring the light of this source during a period of 10 minutes or so, we observe this dip at some point, just to eliminate possibility of, say, a cloud passing through and causing the asteroid and star to dim. We actually measured the brightness of a nearby star, and there's nothing there. So we think this is the effect of the asteroid actually hiding the star. Okay, so that's basically what I had to do about what I had to say about asteroid occultations. I'm going to switch to a similar phenomenon, which is an eclipse of the moon. Now, this takes place when basically the Earth comes between the moon and the sun. So the moon will enter the shadow of the Earth. Just like I show here, I took that from Fred Espegnac's website. Okay, but our geomet has not. It's not restricted to the moon and the Earth. When you have a planet like Jupiter or Saturn or Uranus that has many moons circling around it, you can actually have a pair of moons playing this game. So, for example, if you have two moons that align with the sun and you observe it from the Earth, you see one of the moons being dimmed by the shadow of the moon in front, and that's an eclipse. Also, if the two moons align with the Earth, you see the disk of one of the moons actually hiding a moon in the back, and that's called an occultation. Okay, so these mutual events do not occur occur continuously. They actually occur in batches, every several years, in fact. So for Jupiter, for example, they occur every 6 years. They are scientifically useful, as I'm going to briefly touch. As a subject, I'm going to briefly touch on just a couple of minutes. So there's actually an organization called IMCC that has organized campaigns to observe mutual events since 1973, and in fact we're going through such a season right now. Okay, so this is a short movie taken by an amateur astronomer in the Philippines, and actually shows you two moons of Jupiter here, and you can see the moon, the bright moon, which is Io, casting its circular shadow on the fainter moon, which is Ganymede. And in fact, shortly after, the brighter moon actually occults part of the top of the fainter moon. Okay, right, so again, there was a team of us here at the observatory who decided to have a go at it with a 10-inch telescope that we borrowed from the planetarium and a video camera. Okay, so we captured 17 events of video. Here's an example of one. So that's basically the final product, the light curve that shows the eclipse. We got about 10 or 11 light curves, and these were finally published in a paper that came out at the beginning of this year. And you can see 4 of the names that I've highlighted are those of students that were at the observatory in 2003. Okay, so right, so a brief touch on the science. Well, there's weird and wonderful things going on in the Jovian system, as in any satellite system, and the core cause of this is basically tides, as in the high tide and low tide that you notice when you live near the sea. So these tides actually leave a very subtle signature in the motions of the planets, of the satellites, which you can detect using observations spread over several decades. And that's what mutual events gives you. It gives you those signatures that in turn can tell you something about what's happening within Jupiter and within Ios, so you can better understand the system. Okay, just a brief mention of mutual events of the planet Uranus, which we observed a couple of years ago, just to show that one of the events we observed took place with a 16-inch telescope that resided in a school campus in the outskirts of Athens. So the light pollution there was quite atrocious, but that didn't actually prevent us from getting a decent light curve. And in fact, that was published again earlier this year. Basically, these Greek names here are my colleagues in Athens who contributed to the observation. Okay, so just to show you an observation that I made just a week ago. You can see here you have a pair of satellites. One is Io and one is Europa, and there's an eclipse going on, and you can see in the middle of the eclipse Europa has visibly dimmed. So these events, at least some of these events, are actually noticeable to the eye, and some light curves we got, and these are subsequently published in a publication similar to what I showed you. Okay, conclusions. Okay, light pollution is not a showstopper in carrying out astronomical observations, but you have to be careful about what you observe. It's always helpful if you talk to the experts, or you know what's possible or useful. You will increase your impact if you're coordinating with other observers, and it's also useful sometimes to be prepared to travel short distances. And, sorry?
For occultation.
For occultation, yes. That's it. So I think I'll stop here. Thank you.
One of the things I was thinking of looking at that is, could you quickly tell us the trade-off? What kind of timing accuracy do you need, and then what kind of magnitudes are you talking about? Presumably one trades off against the other for your small telescope.
Are you talking about asteroid occultations or sort of mutual events and things like that? Well,
what's available
for asteroid occultations? Well, light polluted sky does not directly interfere with the timing. Okay, of course, if the sky is bright, that gives you constraint on how long you can expose for. But now, I mean, there are very sensitive video cameras and also GPS time inserters that can reach down to, say, magnitude 11 with an 8-inch.
So just run them at video rate.
Yes, that's right. And the GPS timestamp will give you a precision of about 100th of a second at least. So you're well covered there.
You reminded me that many years ago, my Amateur Astronomical Society attempted to follow on a story from Sky and Telescope, where a guy had got a 2-mile cable and 70 stations on a chart recorder so that they could work out the profile of the moon at an edge occultation. And it struck me that with the modern communication that kids now have, practically every kid has got a mobile phone, the kids could work out the lunar profile as the moon obscures, say, Jupiter, which wouldn't be too badly affected by sun city light pollution, And I'm thinking people like Ron Hill and Connie Walker could physically get this idea that you're talking about back on the agenda from a practical perspective. And it strikes me as an ideal idea to pick up on what you're telling us and take it to schools with something like the moon and something as bright as Jupiter.
Yes, I mean, if you pick the target carefully, I mean, then you actually do great science with just organizing.
I wanted to point out about asteroidal population that there will be next year on July 8th famous event, and you have a poster there, and it's involved a bright star visible to the naked eye, and it involves all Europe.